It's good to be with you once again. Today, we're going to talk about tangent planes and linear approximations. This is a direct extension of what we learned back in the first term of calculus, where we talked about tangent lines and linear approximation using those tangent lines. So let's dive into it. Let's see how all this applies when we have more than two dimensions in play. Tangent planes and linear approximations. Let's start with a review. Recall from when you were first learning calculus that we sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at the point. The idea is that if we zoom in far enough toward the point, the curve looks almost like a straight line. For example, in the pictures below, we zoom in on the curve of y equals x squared near x equals 1. The more we zoom in, the more the parabola looks like a line. In other words, the curve becomes almost indistinguishable from its tangent line. You can see that there's a curve here on the first graph, and then we zoom in closer. You can see that in the first graph, we're going 0 to 2, 0 to 2. In the second one, a half to 1, 1/2, a half to 1.5. And it's beginning to look a lot straighter. And then in the last case, it looks just about like a straight line as we've zoomed in. And so now our window is much smaller, from 0.9 to 1.1, 0.9 to 1.1. Later, we built upon this idea of a tangent line in order to approximate functions. The idea is that it might be easy to calculate a value of f of a function, that is the function value, but difficult or impossible to compute nearby values of f. So we settle for the easily computed values of the linear function L, whose graph is the tangent line of f at a comma f of a. In other words, we use the tangent line at a comma f of a as an approximation to the curve y equals f of x when x is near a. An equation of this tangent line is y equals f of a plus f prime of a times x minus a. And the approximation f of x is approximately equal to f of a plus f prime of a times x minus a is called the linear approximation or tangent line approximation of f at a. The linear function whose graph is this tangent line, that is L of x, equals f of a plus f prime of a times x minus a. Here we have it in the picture. So the red curve, this is our y equals f of x. The green line, this is our tangent line. And instead of just calling it tangent line or something along those lines, we're just going to give that tangent line a name. We're going to call it L of x because it represents that linear approximation. So L of x is just the tangent line. It's just a new name for the tangent line. To make sure we understand this, let's look at an example. Example 1. Find the linearization of the function f of x equal to square root of x at a equals 4, and use it to approximate the square root of 4.1. So if we're going to do a linearization, then we need a point, and we need a slope. So our point is going to be 4, comma, square root of 4, or 4, comma, 2. Our slope is going to be f prime of 4. And again, we're using the 4 because that's our a. F prime of 4, which would be 1 over 2 root x, evaluated when x equals 4. That would be just 1 over 4. So our linearization, so L of x is going to equal the y value of the point, which is 2, plus 1 over 4 times x minus 4. Let me make sure you see this in color. So here's the 2. Here's the 1/4, which is our slope. And here's the 4 showing up in that equation. If we want to approximate the square root of 4.1, say, and the square root of 4.1 is approximately equal to L of 4.1, which would be 2 plus 1 over 4 times 4.1 minus 4, which would be, this is 0.1, a quarter of 0.1, so that would be 2.0025, if I did my arithmetic correctly. And we could check that against the calculator. So I have my Texan friend here, and I'm going to find the square root of 4.1, and the square root, that looks like I have an extra 0. Sorry. So I checked it to verify my arithmetic. I have an extra 0, be 2.025, because it'd be a quarter of 0.1, not a quarter of 0.01. So this is our approximation. The actual value is closer to 2.0248. So this is a pretty close approximation to the square root of 4.1, which is pretty cool. Again, it's an approximation and not the exact value, but it's pretty cool. It means by hand, assuming we do our math right, which I lost it on my arithmetic there for a moment, we can estimate some square roots, especially ones that are nearby known values. In this section, we develop similar ideas in 3D. As we zoom in toward a point on a surface, that is the graph of a differentiable function of two variables, the surface looks much more and more like its tangent plane. We can approximate the function by a linear function of two variables. Let's look at a manipulate so that we can see this zooming in process. So here we have some sort of a saddle shape, nice smooth surface, and we want to zoom in on the region that's inside this box. Notice as we zoom in, that curve, that's very curvy looking saddle begins to look flatter, flatter, flatter. We're zooming in, and we're zooming in, we're zooming in. The boxes kind of give us the sense that we're zooming in. And notice the red and the blue lines are getting straighter and straighter and straighter. So to the end, where here we are when we've zoomed pretty far in, and it looks like at that point, it looks like our nice curvy saddle is just a plane. Let me go back out. So see the curve of the red line and the curve of the blue line. But as we zoom in, again, zoom in far enough, we start to see that it looks like a plane. Not just a line, not just a tangent line, but an actual tangent plane. So let's try to understand this new concept of a tangent plane. Recall that if C is a smooth parametric curve in 3D, then the tangent line to C at a point P naught is the line through P naught along the unit tangent vector to C at P naught. And so here's our curve that we're talking about. Here's our C. Okay. And then right at that point P naught, here's our P naught, we have this unit tangent vector, which we called our T vector. The concept of a tangent plane builds on this definition. If P naught is a point no longer on a curve, but now it's on a surface, and if the tangent lines to P naught to all smooth curves that pass through P naught and lie on the surface of S all lie in a common plane, then we shall regard that plane to be the tangent plane to the surface S at P naught. We can see that in the picture below. So notice that our P naught is the point right in the middle. There's our P naught. And we could look at a whole bunch of curves that all go through that same point. Okay, and all of those curves have little unit tangent vectors all at P naught. And so you could picture and think, gee, all of those little unit tangent vectors are all on the same plane, all on the same tangent plane. A tangent plane that'll look sort of like this one in the picture on the right. So here, my P naught would be this point in common. And you can see that even though they're a little bit underneath, but you can see you'd have lines kind of cutting through. You could see those lines coming through, and that the tangents right at that point would be along the given plane. So we have this beautiful idea of a tangent plane showing up to a surface. Let's look at a couple more manipulates to see the picture of this tangent plane. So here again, what we're trying to see is the shape or the visual of a tangent plane. What I want you to notice is that this plane sitting on the surface of the cone and just barely is touching the cone right at that point, right? It's just tangent to it. So it just barely touches, and it perfectly captures the slope in all directions right at that one point. So you can imagine those little unit tangent vectors, right? That all the unit tangent vectors in all directions at the point would all be on this tangent plane. Or here's another picture with the same. So it's a different surface. This one has kind of a hole in it, and you'll notice right at that tangent or the point that we care about, -1, 2, 1 in this particular case, that the plane and the curve are sharing perfectly their slopes. It's like they're just barely touching each other. And so there's sort of this sense of adjacency. It's just like the tangent line, that the closer you would zoom in, the closer the plane and the curve would look to being identical. So I hope that gives you a picture of what a tangent plane looks like. Definition. We say that z equal to f of xy is differentiable at x naught, y naught if the partials fx and fy exist near x naught, y naught, and the partials are continuous at x naught, y naught. So a couple logic questions just for fun. Is it possible for a function z equal to f of xy to be differentiable at x naught, y naught, even though fx and fy do not exist at x naught, y naught? So the answer here is no. And the reason is because they have to be continuous, because fx and fy are continuous at x naught, y naught. Second logic question, again, just for fun. Is it possible for a function z equal to f of xy to be non-differentiable at x naught, y naught, even though fx and fy exist at x naught, y naught? And the answer is yes, it is possible, because the partials could exist at the point, but not exist in the area around it. So yes, fx, fy could exist at x naught, y naught, but not in the area around it, but not in the nearby area. So the first of these got at the continuity part right here, and the second of these got at the near part. Continuous, the nearby area part. So just a couple of questions helping us to see what's going on in that question. I mean, in that definition. The tangent plane to the surface S of a function z equals f of xy at p naught, which is x naught, y naught, z naught, exists if and only if z equal to f of xy is differentiable at x naught, y naught. But how do we find this tangent plane? Suppose we are given a surface z equals f of xy and asked to find the tangent plane at point p naught, which is x naught, y naught, z naught. We recall that finding the equation of a tangent plane requires that we know a point, which we already have, and a normal vector. So to find a normal vector, notice that at a given point of the partial derivatives, at a given point, the partial derivatives point along the plane in the x and the y directions. So specifically, in the x direction, the slope of fx at x naught, y naught, or the slope is fx of x naught, y naught, and the vector would be as follows. So we're going to let things change in the x direction, no change in the y direction, and the slope would be show up in the z component, fx, x naught, comma, y naught. The slope in the y direction. So the slope is the partial derivative of f with respect to y at x naught, y naught. And the vector would be no change in the x, one change in the y, and fy at x naught, y naught. And so if we want to find the normal vector to the point, or a normal vector to the point, to the plane at point p naught, we can simply use our cross product, and our cross product will be, let's see, it'll be 0 minus fx, and then there's the minus sign that's built into the formula. So we would have minus fy, and then 1. So we have a normal vector to the plane at the point p naught, and we found that by taking advantage of what we know already from partial derivatives. Recall, the scalar equation of the plane through the point p naught, x naught, y naught, z naught, with normal vector n, which is a, b, c, is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. So in our particular case, our normal vector, ABC, which shows up here in the equation, is given by that normal vector that we found above from the cross product, and our point is the same in both cases. So our tangent plane would be minus fx times x minus x naught minus fy times y minus y naught plus 1 times z minus z naught equals 0. And here's those yellow values. And this is a little bit confusing because it looks like fx evaluated, and so we don't like this notation. So let's use better notation. So which is better written as, so if we take these two terms and we write them on the other side of the equal sign, we would have z minus z naught equals fx at x naught, y naught times x minus x naught plus fy evaluated at x naught, y naught times y minus y naught. So here's the yellow parts showing up. And so again, thus the equation of the tangent plane is z minus z naught equal to the partial derivative of f with respect to x, evaluated at x naught y naught, times x minus x naught, plus the partial derivative of f with respect to y at x naught y naught times y minus y naught. Example 2. Find the equation of the tangent plane, called a tangent plane around here. Find the equation of the tangent plane to the surface f of xy equals x cubed y at the point 2, 1, 8. So to do this, we need to find fx of xy, which will be 3x squared y. And then we're going to evaluate this at 2, 1, which would be 3 times 4 plus 1, 4 times 1, 12. And we also find partial derivative with respect to y of xy. So that would be x cubed evaluated at 2, 1, and that will be 8. And just double checking my math before we keep going. Okay. And the plane is, so it would be z minus 8 equals 12 times x minus 2 plus 8 times y minus 1. Let's see if we can see these things in color. So the 12 is showing up here, 8 showing up there, and the point 2, 1, 8 is showing up 2, 1, and 8 there. So this is our tangent plane. Here's our tangent plane. Yay. This next exploration helps us to again see the tangent plane through the zooming process. So let's explore f of xy equal to x squared y with graphing software, and we're going to use 4 different windows. So in the first case, we'll go negative 27 to 27 in the x, negative 27 to 27 in the y, negative 27 to 27 in the z. And when we do that, we get a graph that looks like this. And we say, wow, that's a pretty crazy shape. Something is happening right there in the middle that's a little bit hard to see and hard to understand. So then we zoom in a little bit more, and we go from 0 to 4 in the x, negative 1 to 3 in the y, 16 or 6 to 10 in the z, and we get a graph that looks like this. And you start to see that tangent plane. You have the curve over in this region, but it's starting to look pretty flat there around where the tangent plane is showing up. And then we could go from 1.5 to 2.5 in the x, 0.5 to 1.5 in the y, 7.5 to 8.5 in the z. And again, you're seeing that center section is starting to look flat, in the vertical part. Okay, as we zoom in, things look flatter and flatter. And finally, 1.9 to 2.1 in the x, 0.9 to 1.1 in the y, 7.9 to 8.1 in the z. And by golly, that curve that was all curvy and wacky looking starts to look very, 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 very flat right at the point that we are interested in. So notice that the closer we get to the point, the flatter the graph of your surface becomes and closer to the tangent plane. That is what we will use to do linear approximation in 3D. I simply wanted to look at those same graphs here live, not on the static page, to just try to help you get a picture for the curviness of the original graph. Here, it's kind of hard to see. It's a little bit crazy wacky, but you can see that there's this funky curve thing happening and the tangent plane on top of it. The curve's a little bit easier to see in the next zoom in. there's that curve showing up, the tangent plane. We'll go a little bit farther in, and you can see that curve showing up. And by the time we zoom all the way in, boy, the curve and the plane look almost identical. In the previous example, we found the equation of the tangent plane to the function f of xy equals x cubed y at the point 2, 1, 8 to be z equals 12x plus 8y plus 8. Notice in this case, I moved the 8 from the z side over to the other side of the equation. This could also be written as L of xy equals 12x plus 8y plus 8. This function is called the linearization of f at 2, 1. The approximation of f of xy, that is, f of xy is approximately equal to 12x plus 8y plus 8. This is called the linear approximation or tangent plane approximation of f at 2, 1. To see how this works, let's find L of 1.9, comma 0.89 and f of 1.9 and 0.89. Let me make sure you see which is which. So L, this is going to be the approximation. And f, this is going to be the exact value. Maybe let's start with the exact value. So if we want to find f of 1.9, 0.89, this would be like 1.9 cubed times 0.89, which we can find Texan style. Let's see, so 1.9 to the third times 0.89. I've got 6.10451. This is the exact value. I didn't even have to, the decimal actually terminates, so it actually is an actual equivalence. So again, it's exact. We could approximate this using L of 1.9, comma 0.89 would be 12 times 1.9 plus 8 times wait a second. Give me a second to check something. We go back to that question earlier. I think I've got a typo in my notes. This should be 12 times x minus 2, 8 times y minus 1. So let's go back and make that edit. So this here should be 12 times x minus 2 plus 8 times y minus 1 plus 8. And that would be our L. Or later on, yeah, in each of these cases, we'd get the same thing. So 12 times x minus 2 plus 8 times y minus 1 plus 8. Or here, 12 times x minus 2 plus 8 times y minus 1 plus 8. All right, so that means we can come back. And we want to find 12 times x, which is 1.9 minus 2 plus 8 times 0.89 minus 1 plus 8. Or this would be 12 times negative 0.1 plus 8 times minus 0.11 plus 8, which is equal to, let's see what we got, 12 times negative 0.1 plus 8 times negative 0.11 plus 8 equals 5.92. And this is our approximation. So the exact number is this 6.1. The approximation is 5.92. And you'll notice that they are both pretty doggone close. So we use the tangent line, and the tangent line gave us a nice way of approximating what was going on with the function. And computers and mathematicians have a much easier job or time working with linear functions than with curvy functions, which is why we like this linear approximation. So note that if we looked at a point from farther from 2, 1, for example, 3, 2, we no longer get a good approximation. So this linearization really is only valuable if you're close to the given point, which in this case was 2, 1. Now let's find a general formula for the linearization of f of x f of xy at AB. So we said that z minus z naught is equal to the partial derivative of f with respect to x at x naught y naught times x minus x naught plus partial derivative of f with respect to y at x naught y naught times y minus y naught. Since z is equal to f of x, y, and z naught is equal to f of x naught, y naught, consider the point AB in 3D, which is a, b, f of AB. So in this case, and I'm just going to highlight as we go just because there's a lot of symbols here, we would say that that z minus f of AB is equal to the partial derivative of f with respect to x, evaluated AB, times x minus a, plus partial derivative of f with respect to y at AB times y minus b. You could shift the f of AB to the other side, showing up here. And so now we would have that z is equal to f of AB plus partial derivative of f with respect to x evaluated at AB times x minus a plus the partial derivative of f with respect to y at AB times y minus b. And we know that this tangent plane is just another name for the linear approximation. So this tells us that the linear approximation of f of xy at the point AB, so L of xy, is equal to f of AB plus the partial derivative of f with respect to x evaluated at AB times x minus a plus partial derivative of f with respect to y evaluated at AB times y minus b. So definition, we say that the linear approximation or tangent plane approximation of f at AB is this function here. The f of xy is approximately equal to f of AB plus partial derivative of f with respect to x evaluated at AB times x minus a plus partial derivative of f with respect to y at AB times y minus b. And note, f is called differentiable at AB if both the partial derivative of f with respect to x at AB and the partial derivative of f with respect to y at AB exist, and the linearization of f at AB closely approximates f of xy when xy is sufficiently close to AB. Example 3. Show that f of xy equal to x squared e to the y is differentiable at 1, 0. Find its linearization and use it to approximate z equals f of 1.05, negative 0.01. So if we want to show that f is differentiable, we simply need to find its tangent plane approximation. To do that, first we will find the partial derivatives. So we know that fx at xy will be 2x e to the y. And when we evaluate this at 1, 0, we will get 2 times 1 times e to the 0, or 2. And we know that fy of xy, partial derivative with respect to y, will be x squared e to the y which when evaluated at 0, 1 would be equal to 1. So this tells us that our linear approximation, L of xy, is equal to 2 times x minus 1 plus 1 times y minus 0 plus, I guess we also need to know f of 1, 0, which would be 1 times 1 or 1. So plus 1. Let's get some color in here. So the 2 is my coefficient on the x minus 1. The 1 is the coefficient on the y minus 0. And the 1 for f of 1, 0 is the plus 1 at the end. The fact that this tangent plane exists, the fact that those partials all exist, tells me that f is differentiable. So the last part of the question is to use this to find the approximation for z equal to f of 1.05, comma, negative 0.01. And so we want to find L of 1.05, comma, negative 0.01. And that would be 2 times 1.05 minus 1, 0.05, plus 1 times negative 0.01 minus 0 would be negative 0.01 plus 1, which looks like 1.1 minus 0.01, I think that's 1.09. We can compare, we definitely makes sense to check. So to check, we will find f of 1.05, comma, negative 0.01 using our text and friend. So I have, let's see, 1.05 squared times e times e to the negative 0.01. And this is, I just have to round because it's, this is I can't give you the exact number here, but I have 1.09153. And so you can see that the linearization, which is the approximate here, is very close to the exact value, which is down below, or at least exact to 5 decimal places. Differentials. Let's begin with a review of differentials. Recall that if y equals f of x is a differentiable function, then we defined the differential of x, defined by dx, as an independent variable. It could be any real number. The differential of y, defined by dy, is then dependent on dx and can be defined by the equation dy equals f prime of x dx. To understand the geometric meaning of this, consider the given graph. So P and Q are on the curve, not the cure, but the curve. Y equals f of x. So here's our P, here's our Q, point right there. They are delta x away from each other in the x direction. So then delta y is the change between their y values. Notice delta y is an exact amount. It's the exact change in the y coordinates between P and Q. R is on the tangent line. So here's our R point. And it is delta, same delta x away in the x coordinate from P and R. And the change between their y values is dy. So here's change in the y values. Okay. And so we get that delta x delta y is the change, the exact change in y. Let me put this in writing. So delta y equals the exact change in y. While dy is equal to the approximate change. Change in y. Okay. So continuing on, what is the slope of this tangent line using rise over run? So the slope of the tangent line using rise over run would be delta y over delta x. Actually, I take that back. That's exactly backwards. I just need to read my own picture. So the slope of the tangent line would be the dy over dx in the picture, because it's the change along the line, which is the green change, not the red change. And then what is the slope of this tangent line using the concepts of calculus? That would be f prime of x. So therefore, dy represents the amount that the tangent line rises or falls. There's the change in linearization for some given delta x or delta y. And on the other hand, delta y represents the amount the curve rises or falls, the exact amount. So once again, we have dy is tied to the tangent line. Delta y is tied to the curve. So one of them is exact, one of them is approximate. It looks kind of confusing. It's actually not that difficult to work with. Now let's take this to 3D. For a differentiable function of two variables, z equals to f of xy, we define the differentials dx and dy to be the independent variables. That is, they can be given any values. And then the differential dz, also called the total differential, is defined by dz equals, let me highlight, dz equals the partial derivative of f with respect to x times xy dx plus the partial derivative of y evaluated xy times dy, or partial derivative of z with respect to x times dx plus partial derivative of z with respect to y times dy. In this latter formula, notice that in the first case, you have partials, and in the second case, you have derivatives. Partials imply that there's more than one variable. Derivatives imply there's only one variable. All this may look intimidating, but it's actually straightforward. The total differential is the change in height on the tangent plane. So specifically, it's the approximate total change. And so if you have some curve, you can think about the change in height from the original point to the final point. So you're going from the original point to the final point. That would be this change, this red change. So this is your exact change. But your approximate change would be following the tangent plane, start at the same point, go along the tangent plane, and your approximate change would be your dz. And finding it requires, I mean, if you think about it, you start at the initial point, you would go along a line that has slope I guess, partial derivative with respect to y, and you'd go along that line a distance of delta y or dy, and then you'd follow another line that has a slope of partial derivative with respect to x, and you go a distance of dx or delta x. And so that's why the dz, or the total differential, would give you that approximate change and have the formula that it does. So if we think about this formula for the total differentiable, and we want to write it in words, what it's saying is that dz, or the approximate change in z, is equal to partial derivative with respect to x at xy times dx. So that would be the slope in the x direction times the change in x, plus partial derivative with respect to y, that's the slope in the y direction, dy, that's the change in y. So remember, it's really important. It's not difficult, but it's a little bit, can be a little bit confusing. Remember that dx is the approximate change. Delta z, I said dx. Remember, dz is the approximate change in height. Delta z is the exact change in height. So one of them requires, this one requires knowing the tangent plane, whereas delta z requires knowing the function height value in two places. Example 4, let f of xy be equal to the square root of x squared plus y squared. A, find the differential dz, or the total differential dz. And so our dz is going to be equal to the partial derivative with respect to x. So that will end up being x over the square root of x squared plus y squared times our dx plus y over the partial derivative with respect to x squared plus y squared times dy. Notice these are all d's, not partials. So if I want to use the total differential that we just found to approximate the change in this function as xy varies from 3.4 to 3.04, 3.98, what I will notice is that if I go from 3 to 3.4, that means my dx is going to equal 0.04, because my x values increased by 0.04. And my y's go from 4 to 3.98. So that tells me my dy will equal negative 0.02. And we also know that our xy is going to be the initial point, which would be the 3, 4. So that tells us, together, all these things tell me that dz is equal to 3 over 3 squared is 9 plus 4 squared is 16. So 25 squared root of 25 is 5. 5 times 0.04 plus, we'll have y, which is 4/5 times negative 0.02, which would be, we use our Texan friend, 6 times 0.04 minus 0.8 times 0.02, which would be 0.008. So it tells us that the function has changed in height, like the approximate change in height of the function from 3.4 to 3.04, 3.98. The approximate change is 0.008. So again, this is the approximate change In C, we're asked, is the value we found in part B close enough to the actual value of the fall rise of the curve at 3.04, 3.98 compared to 3.4. So here, what we want to do is we want to find the actual change, delta Z. Ooh, that's a scary looking delta. Delta Z, which will be equal to F of 3.04, 3.98 minus F of 3.4, which, if I do this Texan style, would be square root of 3.04 squared plus 3.98 squared minus the square root of 3 squared plus 3 squared plus 4 squared. And all that is to 5 decimal places, 0.00819. This is our, to 5 decimal places, this is our exact change. So we're wanting to know, are these things comparable? Yes, I think that the total differentiable is comparable to the actual change in the function. Last section in this topic. So functions of 3 or more variables. Linear approximations, differentiability, and differentials can be defined in a similar manner for functions of more than 2 variables. In particular, if w is equal to f of xyz, then the differential or total differential dw is given by dw equals the partial derivative of w with respect to x times dx plus the partial derivative of w with respect to y times dy plus the partial derivative of w times dz, or of w with respect to z times dz. So in example 5, we want to find the differential of the function, or the total differential of the function L, equal to xz e to the negative y squared minus z squared. And so our formula is above. So we're going to find dl, and it's going to equal the partial derivative of L with respect to x, which would be z e to the negative y squared minus z squared times dx plus the partial of L with respect to y, which looks like it's just going to require a chain rule. So we're going to have a x, z, the derivative of the inside is going to be a minus 2y, e to the minus y squared minus z squared, dy. And then we have plus the partial derivative of L with respect to z. This is going to require the product rule. So we're going to have x e to the minus y squared minus z squared. So that's when we take the derivative of the x times the other part, plus derivative of the part that has the e is going to be an x z negative 2z e to the negative y squared minus z squared. Okay, all that dz. Let's see if we can see this in color. Let me recolor the formula that we're working from. So partial derivative of w with respect to x, that's this z e to the negative y squared minus z squared. Partial derivative of w with respect to y, that's going to be our xy times negative 2y e to the negative y squared minus z squared. And the partial of w with respect to z, that's this whole product rule mess. And then we multiply by the differentials, the independent differentials, the dx, the dy, and the dz. Altogether, this would give you dw, or in our case, dl, the total differential. So there you have most everything that you need to know about tangent planes and linear approximations. And I hope you can see that this is a direct analog to what we did back in 2 dimensions. And I think probably the most challenging thing is just remembering that the DZs are the exact change, and the delta Z's are the exact change, and the DZs are the approximate change. So delta is exact, D is approximate in this case. Otherwise, it's pretty straightforward stuff, and hope you had fun with this lesson. See you next time.